start looking at special triangles. These special triangles will give us some exact values so that we don't have to have these very long decimal places. We can actually look at the exactness of an answer instead of something that we round. Okay. Let's start with if we had a right triangle ABC and sine B was equal to 3/8. So let's draw it out because just like before, one of our strategies is to always draw a picture, see what we're talking about. So let's say this is A, this is B, and this is C. They're telling me that the sine of B equals 3/8. So sine B equals 3/8. Well, I know sine in a right triangle is always equal to opposite over hypotenuse. So that must mean that my opposite side of B must be 3 and my hypotenuse must be an 8. What they're asking for me to find is the cos value of B, which I know is my adjacent side over my hypotenuse. So I have my hypotenuse, it's 8. But I need to figure out what this missing side is right here, which is my adjacent side to angle B. This is the angle that we're looking at. Okay, so when I know two sides of a right triangle and I'm looking for my third, I can use Pythagorean theorem in order to help me solve. And so let's call this, I don't like that we've used ABC, but that's okay. So I'm trying to find that question mark. That's one of my shorter sides. So let's call it C squared plus, and then it's B squared equals A squared. If I rearrange Pythagorean theorem right, remember it's always equal to your hypotenuse squared. So it's side squared plus side squared equals hypotenuse squared. All right, and the side that we don't know is C. We don't know that side C. I do know side B, which is 3, and I do know my hypotenuse, which is 8. So C squared plus 9 equals 64. C squared is going to equal out, I'm going to subtract 9 from each side. That gives me 55, and the square root, and I'm just going to leave it as the square root of 55 because we are looking for an exact value. So I don't want a decimal place, but I can't find the square root of 55. It doesn't work out nicely, so I'll just leave it like that, which means that cos B must be that adjacent side, which is square root of 55 over 8. Okay, so that was just kind of remembering Pythagorean theorem a little bit in order to help us find that missing side, and then just writing out our primary trig ratio. All right. Normally we get these inexact answers. We get these big long decimal places, but it is possible to record some of these answers in exact form. So for example, the sine of 75 in your calculator does come up as 0.9659. But actually, it can be written as an exact value of the square root of 2 plus the square root of 6, all divided by 4. And that's what we want to look at, is can we kind of figure out these exact values? So there's a few different angles we're going to look at that give us some exact answers. All right. So we're going to look at the 45-degree angle to start. So I'm going to get you to draw a unit circle. A unit circle is just a circle that has radius of 1. So obviously, you want to draw it big enough that you can input some information in. So maybe if you use something that has a nice big radius on it, and then just say that it's equal to 1. That will work. So draw a nice big circle. But it has a radius of 1. So what that means is if this was my y-axis and this was my x-axis, then this point right here would be at 1, 0. This point up here would be at 0, 1. This point right here is at -1, 0. and this point down here is at 0, -1, and then you just draw a circle around it. Okay, so draw a line from the origin of the circle at approximately 45 degrees. So we're going to start here. I'm going to draw this nice triangle out, and I know this is 45 degrees. Then it says to draw a line from the circle and the line to the x-axis. So what that means is you want to go to where it hits your circle and go straight down to your x-axis to create this 90-degree angle. Now, here's what's interesting. I know that if I have two angles inside of a triangle that I actually have the third angle too. So if one of my angles is 90 and the other is 45, that means that this angle up here must be 45. I also know, since this is a unit circle, because we drew it as a unit circle, that it has radius of 1, which means this has a side length of 1 right here. And then I want to figure out my other two side lengths. Now notice this is an isosceles triangle, which means that whatever my side length is down here at the bottom has to be the same side length as what my vertical line is. So let's call this, let's say this is A, side length A, then this also has to be side length A. Because of it, it's an isosceles triangle. And if I use Pythagorean theorem to figure it out, what I end up with is a squared plus a squared equals 1 squared. And a squared plus a squared is 2a squared, which equals 1 squared, which is equal to 1. Divide by 2, so those cancel. And I get a squared equals a half. And then I can take the square root of each side. And when you take the square root of a fraction, really you're taking the square root of the top and the bottom. And the square root of 1 is 1. And the square root of 2 can stay as the square root of 2. So what we have then is this 45-degree triangle where I have exact side lengths of 1 over root 2, 1 over root 2, and 1. Okay, so that's looking at it inside of a unit circle. We can also take a look at the same thing with a square. So here we have a square. If I draw a diagonal right here, that automatically puts these two angles as 45 degrees. And now if I want to solve for my hypotenuse, so over here is what I'm looking for, this hypotenuse, I have 1 squared plus 1 squared equals c squared. 1 plus 1 equals c squared. 1 plus 1 is 2. Square root of 2, square root of 2. So c equals square root of 2. Okay, so what this gives me is this triangle. So 90, 45, 45, 1, 1, root 2. And you may say, well, geez, that's different than what we just looked at on the previous slide, because on the previous slide, I had, oops, that's not 45. If I pulled out that triangle, that's 90, that's 45, that's 45. I had 1 over root 2, 1 over root 2, and 1. So you may be saying, well, they're different, but they're actually not. They're actually equivalent. If I multiply all sides by root 2, then what I get is root 2 times 1 over root 2, which just equals out to 1. And 1 over root 2 times root 2, which just equals out to 1. And 1 times root 2, which is just root 2. So they're actually exactly the same. So either one of those triangles will work because they give you the exact same answer. Okay. So using either or, I'm going to use my top one here, just because it's a little less messy. So this is the one I'm going to use right here. If I was asked to find the sine of 45 degrees, what I would do is go to either one of the 45-degree angles. It doesn't matter which one. They're going to give you the same answer anyways. And I know that sine is opposite over hypotenuse. So I'm going to go to, let's say I'm going to use this angle here. My opposite side is 1. And my hypotenuse is root 2. So 1 over root 2. Okay, and if I go to cos, which is adjacent over hypotenuse, my adjacent side is 1 over a hypotenuse of root 2. And tan is equal to opposite over adjacent. So my opposite side was 1, my adjacent side is 1, and 1 divided by 1 is 1. So these are the exact values for those angles. So if you go to your calculator and you type in sine 45 degrees, you get 0.707106 on and on. But the exact value to that is actually 1 divided by the square root of 2. Okay, if you go to tan 45, notice you get 1. Okay, so that works out. You get a 1. So these are our primary trig ratios for sine, cos, and tan of 45 degrees. Now this triangle, you're going to need to have in order to help you answer questions. So 45, 45. I always like to remember this as the 1, 1, 2 triangle. Okay, that's how I remember it. So 1's on either side, and then the square root of 2 as my hypotenuse. All right, so 45 is definitely one of our special angles. But 30 and 60 are also special too. So again, draw a unit circle, so radius of 1. Make it nice and big so that we can see stuff on it. And then from there it says draw a 30-degree angle. So 30 degrees, I'm just going to eyeball this. I'm going to say like this is 30 degrees. I know that has a radius of 1. And then a negative 30. So negative 30 means we're going to go down. Also has 1. All right, so if this is 30, this is 30. And then what I'd like you to do is I'd like you to connect these with your x-axis. Oh, come straight down like that. Now, this creates a 90-degree angle inside that triangle. So 30 and 90, which means this is 60. And then this creates a 90-degree angle in this bottom triangle, 30 and 90, which means this is 60. All right. So let me pull this out so it's a little bit easier to see. This is what we have. So we have 1, 1. We have 60 up here in the corner, 60 down here in the corner. And then those two 30s also make a 60, which means this is an equilateral triangle. And if it's an equilateral triangle, it has to have side length 1 over on that third side too. All angles are the same. All side lengths are the same. And so if I just go over back to my diagram, if this whole length is 1, that means to split those two triangles into 2, each of those lengths must be 1/2. All right, so again, I want to pull this out so that we can see it just a little clearer. I have 90, I have 60, I have 30. This is a 1, this is a 1/2. Down here becomes my question mark. So I want to be able to figure out what that angle or what that side length is. And I'm going to use Pythagorean theorem. So I'll say a squared plus 1/2 squared equals 1 squared. So a squared, a squared plus. Now that squared touches the numerator, so 1 squared, which is 1, and the denominator, 2 times 2, which is 4, equals 1 squared, which is 1. And then I'm going to move that 1/4 to the other side, subtract it. 4 over 4 minus 1 over 4, which is 3 over 4. Okay, so a squared is equal to 3/4. And then, of course, I'm not looking for a squared. I'm just looking for a. So I'm going to find the square root of the top and the bottom. We'll leave root 3 as root 3, but the square root of 4 is 2. So this is going to be root 3 over 2 right here. So this is now my special triangle. It's my 30, 60, 90 triangle that has side lengths of root 3 over 2, 1/2, and a hypotenuse of 1. There's another way, though, that we can figure out this special angles, though. So let's take a look at that. Here we have an equilateral triangle, side lengths 2, 2, and 2. And I'm just going to cut it right down the middle. And if I do, I get 60 there, 60 there. Again, here's my 90, which makes this a 30. It makes this a 30. Okay, so if I split it down the middle, what I have is 90, and I have 60, and I have 30 up here. This is 2. This would only be a 1, because half of 2 is 1. And then this is the length that I'm looking for right here. So same thing as before. A squared plus 1 squared equals 2 squared. A squared plus 1 equals 4. A squared equals 4 minus 1. A squared equals 3. Square root. A is equal to the square root of 3. So this is equal to the square root of 3. All right, so here's my right triangle. And this is the one I use more often than the one on the other slide. 60, 30, and then this is a 1, this is a root 3, and this is a 2. So I like to call this one my 1, 2, 3 triangle since it has a 1, 2, and a 3 in the side lengths. And this is the one that I usually use when I'm finding my primary trig ratios. I just like how it's set up, but it's equivalent to the one on the previous slide. So you can use whichever that you like first. Okay. So now because we have two different angles, we have 30 and 60, we can find the sine and cos and tan of the 30 and the 60. So let's start with 30 degrees. 30 degrees is up here in my top corner right here. So I know that sine is equal to opposite over hypotenuse. My opposite of 30 is 1. My hypotenuse is a 2. So sine 30 is equal to a half. Cos 30 is adjacent over hypotenuse. My adjacent side to 30 is square root of 3 over hypotenuse of 2. And my tan of 30 is opposite over adjacent. So my opposite side is 1, and my adjacent side is root 3. So those are the exact values for sine of 30, cos of 30, and tan of 30. Okay, same thing now, except we're going to use our 60 degrees. So our 60 degrees is down here. Sine is opposite over hypotenuse. So my opposite of 60 degrees is going to be the square root of 3 over 2 is my hypotenuse. Adjacent over hypotenuse, so the cos of 60, my adjacent side is a 1 over a hypotenuse of 2. And tan is opposite over adjacent. So my opposite to 60 is the square root of 3. And my adjacent to tan of 60 degrees is a 1. There we go. Okay. So again, these give us all our exact values instead of our decimal values for the ratio that comes up using those angles, right? So we have two triangles that we use, but it has three angles, 45, 45, 90 triangle, and then the 30, 60, 90 triangle are our two triangles that we're going to use over and over again over the next few lessons. All right, so here they are here. I've just written them out again. Now I try to remember them because the 1, 2, 3 triangle, the root 3 goes by the 30 degrees. So that's how I remember it. But whatever kind of you want to do to help yourself remember these, or just have them written down somewhere nice and neat, clear in your notes to use when you need them. Okay, so we can use this to solve for some problems. One is determine the area of a triangle. So this is our 30-degree triangle, which means that this would be 60 up here. And I'm just going to go ahead and fill in the side lengths according to the 30, 60, 90. So remember I said root 3 and 30 always go side by side. This is normally a 1. This is normally a 2. Okay, but notice it's not a 2 on that hypotenuse. It's actually a 10, which means I would have had to have multiplied that 2 by 5. So that means this needs to be multiplied by 5, and this needs to be multiplied by 5. And now when I find the area of my triangle, I know it's base times height divided by 2. I can see that my base is 5 root 3 times my height, which is 5, divided by 2. And that's going to give me 5 root 3 times 5 is 25 root 3 over 2. And that would be my area for this triangle. My exact area for the triangle. Okay, so we want to use our special triangles when we're looking for exact values. So this is a good example. All right, just one more thing to look at with this unit circle. So remember, unit circle we said has a radius of 1. And we talked about like this point right here is at 1, 0. And up here on my y-axis is 0, 1. And then down here is at -1, 0. And then down here is at 0, -1. So whenever we have some kind of angle in here, so let me go like this. This is along my x-axis, and this is along my y-axis. So this point up here is x, y. But if I put in theta in here, oh, and I know my hypotenuse is a 1 because it's a unit circle. Then if I wanted to find sine theta, I could say, well, sine theta, I'll just write it maybe over here. Sine theta is equal to my opposite side, which is y, over my hypotenuse, which is a 1, which means that sine theta is equal to a y, whatever my y coordinate is. Same thing with cos theta. Cos theta is equal to my adjacent side, which is an x, over my hypotenuse of 1. So cos theta is equal to x. And what this means is that any xy coordinate can also be written, if you know the angle, can be written as cos theta, because that's my x, sine theta, because that's my y. Which is really neat. I think that's really neat. And then tan, of course, is opposite. Tan theta is opposite over adjacent, which is y over x. And since y we said is sine and x is cos, it can also be written this way. So over here, sine theta is equal to your y coordinate. Cos theta is equal to an x coordinate. And tan theta is equal to y over x, or sine theta over cos theta. And the neat thing is that when we're looking for exact values, let's say of 0 degrees, so sine of 0 degrees is just going to be whatever my y coordinate is of 0 degrees. So my y coordinate of 0 degrees, if I just take a look at my unit circle again, 0 ends up right here. So we're looking at this point here. My y coordinate at that point is 0. And my cos of 0 is just my x coordinate, which is a 1. And then sine of 90 degrees. So if I go to 90 degrees will be way up here. So it's this point up here. So my y coordinate of 90 degrees is going to be a 1. And then my x coordinate of 90 degrees is going to be a 0. Same thing with sine 180. So 180 degrees is over here on the negative x axis. So my y coordinate for sine of 180 is going to be 0. My cos of 180 is going to be a -1. And then my sine of 270, 270 is along the negative x-axis, negative y-axis down here, is a -1. And my cos of 270 is my x-coordinate, which is a 0. So then, if I want to figure out my tan, remember tan is always equal to sine over cos. So in this case, sine was 0, cos was 1, and it equals out to 0. And then the tan of 90 degrees is going to be sine, which was 1 over 0. We can't have 0, so it's undefined. Tan of 180 is going to be sine, which is 0 over cos of -1, which is still 0. And then the tan of 270 is equal to the sine of -1 over the cos of 0, which is undefined. Okay, so if you're ever asked to find for like 0 degrees, 90, 180, and 270, those are also special angles, and we use our unit circle to help us. And we're just looking at our x coordinates and our y coordinates of that unit circle, because we know that sine is going to be the y coordinate, x is going to be the cos is going to be the x coordinate, and then tan is equal to y over x. Okay, this stuff takes practice. So go ahead and practice, and if you have any questions, reach out and ask.